All right, welcome everybody to week 3, day 2 of Computer Science 26, Discrete Math. We are going to finish our 3-week tour of modular arithmetic with hashing. So what we've used modular arithmetic before is addition, subtraction, multiplication, and everyone's favorite, division. We've talked about using modular arithmetic, especially POW-M, exponentiation plus modulus, to do RSA encryption. Which, basically, encoding it is just a POW-M call. You take your secret message, which is just an integer, it's a big integer, raise it to the eth power, which is always 65537, modulus it by n, which is both e and n are publicly available. And so that allows anybody in the world to take a secret message, raise it to the eth power, modulus it by n, and send it to you. And then the only way you can decrypt it is by taking that same secret message, raising it to the dth power, which is a secret number, modulusing it by n, and you will get the original message back. So as long as you keep the d secret, then you and only you can decrypt the message unless they can factor n. So as long as n is a really big number that doesn't have some of the weaknesses that we talked about before. For example, if you have a small d, more than a third below the fourth root of n, meters attacks possible. If your message is too small, or if you send a message that can be easily guessed. These are all attacks that are possible. Okay, so also we talked about using cryptographic hashes. There's SHA-1 and SHA-2 and SHA-256 and MD5, some of which are good, some of which are bad, and basically their whole thing is they use the power of like XORs and bit shifts and modulus and things like that to generate a signature on a file. So you can publish a file and have a signature associated with it so that you know if the signature matches that no, not you. If the signature matches, then you know the executable either hasn't been tampered with or somebody tampered with the website as well. So one or the other. Right, so when you go to download PuTTY, there's an executable here, and there's a signature attached to it, and that signature, you can run that same algorithm on the installer and see if the signature matches. Of course, if you're downloading it from the same place, there is absolutely no point to doing that, because what you download comes from the website and the signature comes from the website, so you know, having the signature in the same place as the download is probably not a great system, because an attacker, if they compromise this website, they can put a virus into this and then have the signature match the virus, right? So all it stops is somebody intercepting this in flight and not intercepting that, which is a very improbable situation. This kind of signature is better when you have like a distributed network. Like let's say you're BitTorrenting and you're getting your stuff from like randos on the internet, then that's a lot more useful because you can go on here and verify the signature pretty easily, and then you can download the executable from a random person. And normally you don't trust random people, but if you download from a random person and the signature matches the one on the PuTTY website, then you know that it's legitimate, because the odds are a lot higher that a random person on the internet will try and give you a virus than it is that they're able to hack the original website and insert a fake signature on there. Okay. What's that? Yeah, go for it. Okay, so Betancourt, what's the flushed emoji there for? Okay, so So we're going to go from all that into regular hashing. regular hashing is, for those of you that have had me for CSI 41, you should know about hash tables. And we talked a little bit about hash tables in CSI 41, namely two different kinds of hashing, linear probing and hashing with chaining. And in this class, we'll learn a couple. I was trying to type something, but your key slipped. I gotcha. Okay. We're going to learn a couple more hashing algorithms, and you will be asked to implement all three of them and to benchmark the three different implementations to see how fast they are. Okay. So, oh yeah, RSA is due today. Did you guys all get it done? Yep, you got it done? All right, cool. Not too bad, I hope. All right, let's just follow the algebra. Great, right now, collect homework from CSI 26 RSA. And there we go. Okay, so hashing. How many people here have never done hash tables before or used hash tables in C++? They're called unordered maps. End up overthinking the assignment. Yeah, it's not a hard assignment. But you've never done hash tables? Betancourt, never done hash table? Okay. Then we'll need to explain hash tables first. Use them for how they work. All right. That's fair. Let's go ahead and jump onto the server here. Then main.cc and up here and talk about unordered map. Okay, so that's this is the hash table class in C++ for the standard library. I think they didn't want to call it a hash table because people make their own hash tables classes and they didn't want to conflict with them. I forgot how they work as well. Okay, so let's talk about hash tables. So hash tables are my favorite data structure. Okay. The reason for that is that they have order 1, insert, search, delete. Okay. They're not good at other things, but they're really good at inserting things, searching to see if they're in there, and deleting them. And since those are your three main operations, if that's all you need, then hash tables are really, really fast. Right? So in CSI 41, I think we did an ELO assignment where we had to process 100,000 chess matches, and so the format was something along the lines of a chess player's ID number, second chess player's ID number, and whether they won or lost, or tied, whether the first person won, lost, or tied. And the system would pull the records for the chess players out of the database that we had. The database you made was a hash table. Pulled out the records, and then would look at the ELO rating for the two players, and then would do an ELO adjustment. So when you win, your ELO goes up. When you lose, your ELO goes down. If you've ever played video games, you probably know what I'm talking about. If not, it's not really important. An ELO rating is just basically a number that you have that says how good you are at chess, or how good you are at League of Legends. Or Tinder has a ELO rating system as well that they don't tell you, but it is secretly Tinder's best estimate of how attractive you are. And so every time somebody swipes right on you, your ELO rating goes up. Every time somebody swipes left on you, your ELO rating goes down. And they try to pair you with people of about equal attractiveness. So the hash table is the best way of implementing that assignment, simply because you do 100,000 searches. Like, well, if there's 100,000 matches, there's 200,000 searches because there's two people in chess, right? So you search for both of the players, pull the data, then you say, okay, did they win or lose? If they won, the first person gets points, the second person loses points. If it's a loss, the first person loses points, the second person gains points, and then you insert it back into the hash table. And you do that over and over again. And so if you use any other data structure, you don't meet the time requirement needed to get the extra credit points. You could do, like a binary search tree, which in math class, technically also the set. Okay. Technically there's unordered set as well for the hash tables. So BST, by comparison, has order login. Insert, search, delete, which is slower, right? So if you have a million entries in the database, then to find somebody in the database using a BST is log base 2 of n, which is around 18 or so, something like that. I don't remember. And so that's 18 times slower than a hash table. Right? So downside to a hash table, downside is that they can be wasteful of memory. But as it turns out, oftentimes a binary search tree wastes more memory because of all the pointer overhead. Just kind of depends. So, a binary search tree's benefit, though, and dent these over. Always sorted. You can't sort. That's another downside. You can't sort a hash table. That's why they're called unordered. Unordered means you don't have any ordering with them. You can see if something's in there, you can get it back out, but you can't print them in like alphabetical order. Whereas for the binary search tree, if you ever want to dump the entire list of chess players and they're sorted by ID, you can just print them out, sorted. It's always sorted. You don't have to spend any extra time sorting them. They're always sorted. So that's nice. So if you care about that, then the BST might be better. Depends on your trade-offs. How often do you have to print the whole database versus how often do you have to insert, search, and delete in it? That's the kind of question I can't answer for you. Why are binary trees so popular if they're slower? Like if you need things held in sorted order, you use a BST. Yeah, that's the main benefit, I think. And then vectors hold the order that the items were inserted in, right? So if you have a list of people in line at a bank, you can't use a hash table for it because it loses the order. That's why it's called unordered map. You can say, is Betancourt in line? Is Jochsheimer in line? Is Vargas in line? Yes, yes, no. But it loses the order that people came to the bank. So you can't use a hash table for like to implement a queue or something like that. Like a queue is literally a line, And a BST can't be used for that either because the BST will sort them by like, last name or whatever. So, there's uses for hash tables. There's uses for BSTs. Vectors hold the order stuff was inserted until you sort it, I guess. So it's order 1, push back, and pop back. So if you insert or delete at the end, is order 1, and then it's order n, insert, search, delete from anywhere. So order n's a lot slower than order login, and that's something that a lot of students don't have like a good intuition for. Logarithm's really, really fast. So for a million, it's like, what was it? 50 times faster? No. 50,000 times faster. It's a pretty big difference. So like order in's pretty fast, and it is. Order in algorithm is actually pretty fast, you know. But order log in for 1,000,000 is 50,000 times faster, and then order 1 is about 20 times faster than that. So it's a pretty significant speed difference, you know, when you use hash tables versus a BST, and then BST versus a vector. And so it's really, really important for you to always pick the best data structure for the job. If you look at some of the people's source code from the Josephus assignment, a lot of people were using vectors just because they understood them, and they were erasing knights from the middle of the vector, which works fine if you've got 20 knights, but you don't meet that 1.5 seconds runtime if you are doing order in operations when it should be order 1, right? Because linked lists have order 1 delete. So, okay. And you can't use a hash table for Josephus because they're unordered. They are unordered. You don't have any ordering in it. So you can know if a knight's in there or not, but you don't have any order of like knight number 1, knight number 2, knight number 3. You don't. So you can't use a hash table for it. You can't use the BSD for it. You have to use either a vector or linked list. Okay. How do you decide which to use if time complexity is the same between two different data structures? If the time complexity is the same, then either you don't care, or you use whichever is easier for you to implement, or you benchmark them and find out if there is like still a running time difference. Because Big O is a very rough and crude approximation that, even though it's rough and crude, it's still really important, right? Because like, let's say the BSD has like some overhead that like causes it to run twice as slow as it should. It's still going to be way, way faster than vectors if you're inserting and deleting from the middle of the vector. You know what I mean? Okay, let's say it's 40 operations instead of 20 like we'd expect. Oh no, 40 is still way, way faster than 1,000,000. You know what I mean? So the thing about Big O is that the difference between log n and n is so massive that by the time you get to any sort of reasonable problem size, and 1,000,000 isn't even that big a number, right? That they just sort of overwhelm any sort of mild inefficiencies. Like even if you're like twice as slow, or you're doing everything twice, you know, when you shouldn't be, it'll still be way faster than a vector, right? Does that make sense to me, Crowley? And if you have two sorting algorithms, let's say, that are the same Big O running time, quick sort, heap sort, merge sort, they're all, I'm sure you guys know this already, but best case sorting time for random data is order in log n. Right? I'm sure you guys all know that already. Given random data to sort it, it's order in log n. Can't do any better than that, provably. And there's three different, at least there's a number of optimal ones. There's merge sort, there's heap sort, quick sort, which is actually not in log n in the worst case time, but people have fixed it to be in log n, so I'll just put a little asterisk there. And so you can run all three of them, right? Heap sort is really easy to implement. You insert everything into a heap, and then you pop it off the heap, and it's sorted. That's it. That's heap sort. You got 1,000,000 integers, you insert them all into a heap of integers, and then you pop them all off, and they're sorted. Merge sort we'll be talking about later in the semester, and it's, a couple lines of code. Quick sort is part of the STL, and you can just call sort, and I'll call quick sort on it for you. So you can try your code using all three methods and just time them and just see which one's fastest. Because there's implementation specific differences, there's caching effects, you can look at how much RAM they end up using, and you can just basically once you get past the Big O level, and you're getting into like, okay, they're all in the same Big O, then you just benchmark them and just see which one's the fastest and which one uses the least RAM, and that's the one you pick. Okay. So, in general, though, for like the big important data structures, like they all have different Big O running times for different stuff. Yeah, and you need to know, like, do you need it always to be sorted? If so, use a BSD. If you don't care about preserving the order that stuff came in, use a hash table. Okay, so how do hash tables work? Because the first time you introduce the topic, it's like, that seems impossible. You should not be able to have constant running time. Inserting searches and deleting. All right. So let's say that I can insert into a table the numbers 0 through 9, just to make life easy. Same principle work. Yep. So you insert something called a key and a value into a hash table. And sometimes the key and the value are the same thing. So like if I'm going to insert the number 9, that's the key and it's also the value. Okay. So the key is what you use to search for. Like for a human, if you're inserting a human into like a customer database, what do you think most databases use to search for people? Like when you look up somebody in a customer database or a credit card database, how do you think you search for the customers in it? Customer ID numbers, yeah. Okay. Social Security, yeah, if you have access to it. And that's the reason why Social Security numbers are used everywhere in databases, is because they are guaranteed to be a unique ID for each person. So they are a unique key, and so people love using Social Security numbers, even though they're illegal to do so. People sort of don't pay any attention to the law when it comes to that. You actually can't use Social Security numbers for that purpose, but nobody pays attention to that anyway. At my college, for the first half of my college career there, our Social Security number was our student ID. And so you would, go up to Wendy's and hand them your ID to swipe it for the payment, and it has your Social Security number right there. And so, well, that sounds like a good idea. Yeah. And I was like, hey, that's illegal, right? And they're like, no. This system has been in place since the 1970s. When they passed the law saying you can't make Social Security numbers an ID, it grandfathered in all the systems prior to 1980. I was like, all right, that's cool, I guess it is legal. It's still a terrible idea to be handing your Social Security number to every random person you show your student ID to. You go to the movie theater, here's my Social Security number. You go to Jamba Juice, here's my Social Security number. This is a terrible, terrible idea. And they... Well, college, this is UC San Diego. And they use the Social Security number as your key. That was what they did to search for you in the database. When you went to Canyon View to buy yourself a sandwich, what happened is you'd swipe it and it would just give the Social Security number to the system. The system would look you up in the system using that key. The key that it looked you up on was the Social Security number, and it was it was guaranteed to be unique because every person has a unique Social Security number. And yeah, it worked, and they didn't want to change their systems, is what it amounted to. And then finally, like, I don't know, I can only imagine there were a number of, like, identity theft cases as the result of you sharing your Social Security number with literally every transaction you made on campus. So, it's ridiculous. Yeah, it is. But they're like, technically it's legal for us, you can't do anything. And I was like, even though it's legal, I guess, yeah, this is a really badly designed system, guys. And so they finally could have made a token that leads to the system. Yeah, there's a lot of things they could have done, and they just didn't do it because the system worked. You know what I mean? And so finally, after I'd been there for about 3 or 4 years, they were like, all right, fine, we'll give everybody a unique student ID. And then they retired the Social Security system, and everybody got their own unique student ID. Like all of you have a unique student ID. And so when you log into Canvas or WebAdvisor or whatever, it is looking you up based on your student ID number. So make the ID the last 4 of this Social Security. Yeah, military did the same thing until 2014. Yeah, it's just it's just really convenient to use social security numbers because they're unique, right? So keys have to be unique because that's what you use to search for the record. So you can only get one record, right? If the key was like first name, Bill, okay, great. 900 bills are at UC San Diego, right? Which one is it? You don't know. Keys have to be unique, right? Username, on our Unix system, all usernames are a key. They have to be unique. And so you can't have two people with the same username. It doesn't work. The DMV way, the DMV way is just to not to use any key whatsoever and to just do an order in search through the entire database every time you start looking something up, apparently. Okay. Values don't have to be unique. Values don't have to be unique because the value is like the entire record. So you could have two people at the same address or with the same first name, whatever, right? So you look somebody up based on social security number, and then it's going to say, okay, your address is 1234 Main Street. There could be like your sister living at 1234 Main Street too. That's the value. So you use the key to search the database, and it returns the value, which is the full record, usually. When you do a database query, you don't have to get everything, but just by default, if you do a database query, it returns the entire record, like a name, address, whatever. Okay. The DMV is using order in square database. Yeah. Okay. So do you guys kind of conceptually understand what a key and a value is? Right? Like a student ID number would be a good key, primary key. Does that make sense? Like it's something that you use to search and pull a record. And it's gotta be unique. Otherwise, who knows? Can you make this file public? Yeah, I'll post it for you. It's just a bunch of notes right now. There's no code. I'm about to get into coding. So let's say that we're gonna let's just do a person, I guess. Class. No, let's do a struct. Let's just do it old school, lazy professor fashion. So what kinds of attributes does a person have? Like a let's say there's a customer database or something like that. Name, okay. Name would be a string name. Age, okay, so int age maybe. Eye color, gender, weight, social security number, credit card number, date of birth. All right, long SSN. Hair color, amount of soldiers in the empire. Okay, we'll just stop there. That's good enough. Okay, so we're gonna have name, age, social security number. Nice. And we're gonna implement a database. Okay. So let's implement a database. So we could do this with a vector, but then if we're gonna search for somebody with social security number 1056789, then you just have to go through the whole vector. You could sort the vector and then do like a binary search through it. But then every time you add or subtract to the vector, you have to resort it. Slow. So we're going to use a hash table. Yeah. And we can either make our own or we can use unordered map. Let's just start off by making our own. Okay. So by default, that will construct to be an empty name, but we'll just actually construct it to error. And the age will be defaulted to -1, and the social security number will default to -1 also, just so if we ever print our database out and we get error, then we know an error occurred, right? So better than an empty string, I think. Okay, so let's do this. So let's do this. Let's do infinite loop. While true, we're going to go into infinite loop, cout, welcome to customer database. Ultimate edition, trademark. would you like to 1. Insert a new customer. 2. Search for a customer. 3. Delete a customer. And we probably should have change a customer as well, but you can basically do that with search and delete and insert, right? We'll just leave it at that for now. Infinite loop, there we go. All right, cool. All right, or for quit. All right. And then we are going to choice equals read. So we're going to read a choice. So 1 through 4. If choice is less than 1 or choice is greater than 3, we'll just in the infinite loop. Okay, so let's do this. I guess we'll do a iStream reference operator, double right arrow, taking in a iStream reference ends and a person by reference p. We need to make this a friend function. So we're gonna overload the double right arrow operator for this. So it is going to, like, if you want to cn into a person, we can overload that, and we are just going to do the following options. We're gonna return ends in there so it stops yelling at us. We're gonna read p dot name. Let's read p dot age. P dot sin read. So if they ever type in a squirrel or something, doesn't like that. Overloaded operator. Yeah, that's fair. Okay. Read a string, please. Thank you. So I'll do that, and then okay. So perfect, Alapisco. Perfect. For those of you at home, that is brilliant right there. DMV checking out the vector when they should be using hash table. You will go into my memes collection. Perfect. Grateful for the struct refresher. Yeah, this should be a class, but whatever. The point of this isn't to do classes. I'm just kind of showing you how to do a hash table from scratch. Okay, so we're gonna do that. Okay, so if choice is 1, then we are going to insert a new customer. So we will say customer C. What a great variable name, huh? So we're going to read person, sorry, not customer. All right. Let's make you a customer now instead of a person. You're no longer a person, you are a customer. Okay. So we're going to read a customer, and then let's just echo it back out. C.name, C.age, C.ascend. Oh, did anybody get the FMT library working on the RSA assignment? Nope. Okay. Bill, age 21, Social Security 111, 111. Bill 21, 111, 111. Okay, cool. So that's working. So this is going to read a customer in from the keyboard, and we just echo the data back out. I don't need you anymore. It's working. So, okay, so now we need to insert it into a hash table. We're going to make a hash table. So to make a hash table, we will do the following. Do we want to ask how big the hash table should be? Nah. We'll just do a maximum of 10. So we're going to make a customer hash table of size 10 using old school arrays. Probably not the best idea. Let's use the C++ array class instead. It's the same thing, but a little bit nicer. This is the C++ equivalent of customer. Okay. Have you guys seen this before? The C++ array class? It's literally the same thing. But you can like get the size of it, and you can use iterators with it and stuff like that. So it's just basically exactly the same as a C-style array, but just better. Okay. So that is preferable. And obviously, if we insert more than 10 customers, we're going to run out of room, and so we're just not going to worry about that right now. Okay. So we're running a customer. And now here comes the hash table insert. Hash table insert. Okay. And so how you insert something into a hash table is where the different hash table algorithms come up. So what we talked about before in CSI 41 was we did two different ways of inserting into a hash table. The first was called linear probing. The second was called with chaining and fire safety capacity. Yeah, probably we should add in a check to see if the hash table's full. But so how do you do it? How do you insert into a hash table? Well, you have to figure out what the key is first. So what should we use to put somebody into the hash table? What should the key be? Remember, a key needs to be unique. There cannot be any duplicate. There can't be any duplicate entries. So obviously, age doesn't work because you could certainly have two people with an age of 20. You know, I'm sure two people in this class have an age of 20. That's not usable for the key. So what do you guys think? The name or the social security? The key is an SSN that can be randomly generated. Nope, we're using their real social number. So I'll just notate that this is the primary key. Okay, so this is what we're going to be, what we will be using to search. Search on. Okay. If it was good enough for UCSD, it's good enough for me. Yeah. Can we do the classic 69 420 6666? All right, so we are going to insert. We're going to insert this customer into our database using their social security number as the key. So how do we do that? How do we find which one of the 10 spots in the hash table we should go into? And the simple answer is modulus. Okay, so the spot we go into is social security number modulus 10. Okay, so if their social security number ends in a 2, we go into bucket 2. If their social security number ends in a 7, we go into bucket 7. Okay, UCSD ID card generator. Don't fix something that's not broken. Yeah. Wasn't that terrible? Like, I was just, as a computer science major, I was just like I kind of get why you don't want to mess with a system that works, you know? Like, I kind of get that. Like, when something works, and it's been working since the 70s, apparently, like, you just, you know, leave it alone, by and large. But, man, dude, like, you got how many thousands of students here, and you're sharing your social security number with everybody? Like, not a good idea. It's just really not a good idea. So, yeah, so what bucket are we going to go to? Pretty simple. We're going to say hash table bucket customers social security number modulus 10. And I'm not going to use 10. I'm going to use hash table dot size is equal to C. Are you mad at me? What are you mad at me about? C.ssn? Oh, we didn't capitalize it. We can fix that. I always find that like when I name variables, they usually change once I start using them, because mentally, when I use them, that's actually how I actually want it to be. You know, so I think it should be c.ssn. So I actually go back in and change my class. Usually, once I start using a class, I usually have a second pass over the class and change the variable names. And so it changed from a person to a customer, and it changed from lowercase ssn to uppercase ssn, things like that. It's pretty normal, at least the way that I code it. Okay, so that's it. Now, you might be asking, well, what if two people have the same last digit in their social security number? And that's what we'll get to in just 1 second. But for now, we'll just say, we'll get to that in a second. Okay. So else if choice is equal to 2, then and we could probably use an enum with this or whatever. Whatever. Okay. We're just doing this super quick and dirty. So else for number 2, we're going to search for a customer. So I'm going to say long ssn equals read. Please enter a ssn to search for. So we are going to prompt the user, what social security number do you want to search for? They'll type in 694206666. And how we handle a collision is the big thing. Okay, so this is QBD, right? To do. That's actually the big question in hash tables. Because for the primary insert, this thing here, it's pretty much the same for every version of hash tables. Like you take the key, you modulus it by the size, and if it's open, you write it in there. For now, we're not even checking to see if it's open. We're just writing it in anyway. I'm sorry, Shahab. Your last name is has the same last digit as mine. You're now overridden. You're out of the database. So clearly, we're not done yet, right? But I'm sort of trying to. I always try and do a really gentle introduction to topics. So, okay. Do we need a second array to keep track of open and closed? Not yet, because right now, if there's a collision, we just overwrite the old person. Okay. So we've got inserting working as long as there's no collision. For the second choice, please enter SSN to search for. They type in some number, and then we'll simply see out hash table. So security number record modulus hash table dot size. Again, we're assuming there's no collisions. And we don't have a double left arrow operator for this setup, so we'll do that. So friend ostream operator double left arrow. Ostream outs customer C, shouldn't it? Because it's a customer, not a person. Customers are not people. Return outs, and then see out. We'll do make it a little interesting name. See that name. Age. SSN. Something like that. And so when we see out a customer, it'll print a little record like that for us. What is a free keyword again? This actually means it's not part of the class itself. This is actually a function that exists outside of the class. Even though it looks like it's inside of the class, it's not inside of the class. It's not a member function. It's a global function, sort of. So this is saying if you ever do a cout with a outs, an O stream on the left side and a customer on the right side, such as here, that's an O stream, that's a customer, then call this function. Okay. And friend grants you access to the private member variables of the class. In this case, we don't have any private member variables, but the reason why we use friend there is because if we don't have it there, then we're saying this operator is a member function of our class, and we can't do it because it would have to be a member function of the OStream class. We can't modify it. So by making it a friend, we're just saying it's a global, but I don't like writing these operator double left arrows and double right arrows out in global space because they're really part of the class. So this is just kind of a nice compromise way of having member functions that aren't member functions inside of the class. Okay, so yeah, but friend in general says grant this function. Like you would do it 1, 2, 3, or 6. You do it normally like this. Like you might have seen it done like this before. This is the traditional way. So friend grants permission to your private and protected. And so you say, so this statement here just says that function, wherever it is, has access to my privates. And then down here, when this thing is trying to access c.name, c.age, c.sn, if these things were private, it would have permissions on them. But to me, this looks a little weird, right? It looks a little weird having a global function out in global space. It's not that weird. I mean, people write it this way. So it's not the end of the world. I just think that since this thing really is basically a member function for customer, it should be inside of customer. But that's just my own take on it. You're free to disagree if you don't like the looks of it. Okay. Should be in the class where it applies. Yeah, I think so too. For sure, friends not food. Yeah, the PETA campaign. Yeah. Okay. Yeah. So now we can see in and see out customers. So this is going to grab the customer from the hash table and output it, and then yeah, that's it. And then else choice is, why do I keep spelling it with an S? It's like turned French all of a sudden. All right. Okay. So delete a customer. Okay. So same thing. We're gonna use the key, right? The key is what we use to search for things for. So we're gonna please enter SSN to delete, and okay. And so we're going to erase it by just sending it back to error, I guess. Okay, so hash table SSN modulus hash table dot size. So that's going to get, so if you type in 69.420.666, that, and you got a hash table of size 10, that's going to go to bucket number 6, and we're just going to set it equal to customer. Open close. I don't know if you guys have ever seen this before, but this is going to make a blank customer. It calls the default constructor essentially on customer, and so it creates. Do we have a default constructor? Yes, we do. This actually generates a default constructor for us. So it creates a new customer, calls the default constructor on it, setting these values here, and sticks it into bucket number 6. Can you set it to null? Nope. These aren't pointers. We could have a hash table of pointers and then null them. Probably a better way of doing this is with optionals. An optional can either exist or not exist. For now, if the customer entry there is error or -1 or whatever, yeah, it's kind of wasteful, right? Because we're filling a hash table with error. It's wasting all that memory. Probably really a better way of doing it would be using the optional type in C++, which allows you to have nothing there or a customer. But yeah, this is not a professional code. I'm just kind of trying to show you guys how a hash table works as simply as possible. And obviously, there's a very, very important part to come here. Okay, so let's just see if this works. I've been coding for a while without testing it, which always makes me a little bit nervous. So let's insert a new customer, and it's going to be Aaron with a age of 103 and social security of 420-66-5432. And it is now in the database. We will search for 420-66-5432. And there we go. We found Aaron in there. And then if we search for 123, it prints out error. So we would need to handle that, obviously. Not found. Again, a better way of doing it is with an optional or something like that. But this indicates there's no record there. And then if we delete Social Security 420-665-432, or we could just type 2, because remember we're not handling collisions at all. Then when we search for 420-665-432, it is now deleted. So Aaron is now gone from the database. Okay. But the reason why I'm doing it this really cut rate and bad way, this is obviously we're only halfway done, right? Is I want to show you guys the essence of a hash table, which is this. Okay. So if your social security number is 1234 and you insert it into a hash table of size 10, you modulus it by 10, you get 4, that's the bucket it goes into. That's how you can do an order 1 insert, search, and delete. Okay. And if you're asking, but wait, what if 2 people have the last digit of 4? That's the big question. Okay. And we're going to learn 4 different ways of doing it when we return after these messages. Okay. So maybe it's maybe he was born with it. Maybe it's Maybelline. I don't know. So should be in the class, yeah. Thanks to our sponsor, Maybelline. Yeah. Okay, so let's go ahead and take a 15-minute break and come back at 11:40. And if with your permission, we'll go till 12:30 today. If any of you have to leave, it's fine. You can pick up the last half hour on YouTube, and I'm gonna kind of talk about the different methods of this, because that's the big question. This part here is going to be the same for basically everything. How you handle collisions is where all the intelligence comes in. When we return after these messages from our commercial sponsor. All right, welcome back, everyone. Hope you enjoyed your break. The big question when it comes to hash tables is how to handle those collisions, right? Because right now we can insert, we can search, we can delete, but if we ever have 2 people who, one person has a social security of 12, the other one has a social security number of 22, if they're congruent, right? They'll go into the same bucket. So, how do you handle that? The basic way is called linear probing. Which means go to the next bucket. Okay. Option number 2 is called quadratic probing. And in linear probing, if the next one's full, you go to the next one, and then you go to the next one, you go to the next one, you go to the next one. Wrapping around if you go off the edge of the array. Quadratic probing is +1, +4, +9, +16, +25. So you go 1 to the right, you go 4 to the right, you go 9 to the right, so on and so forth. Okay? And until you find an open one. Then there is what's called double hashing, where you go plus some function to the right, and the function is we'll talk about it in the PowerPoint presentation. Do you guys understand what this means? So like go to the next bucket, we'll say +1 +1 +1 +1 +1, checking all buckets to the right. Do you guys understand my terminology here? So if it hashes to bucket 5 and it's full, then you check bucket 6, then you check bucket 7, bucket 8. With quadratic, if 4 is full, you check bucket 5, you check bucket 8, then bucket 13, which is bucket 3. So quadratic hashing is you go further to the right each time, and only works up to 8% rate. So once the hash table is more than half full, quadratic probing no longer works, which is a pretty significant downside. It can go into an infinite loop or not find open spots once it's half full. Double hashing involves moving some function to the right, and what function is that? Well, we'll go into that in the slides. Okay, so we will start off by just doing linear probing, I guess. Oh, and then there's also chaining. Each bucket is a DST or linked list, but I don't know why people use a linked list. So you just call DST insert on the bucket. So basically, instead of having an array of customers, you have an array of binary search trees of customers, and then you go to the right bucket and you call insert on that binary search tree. So you've got a forest of trees essentially, and that gives you better performance. Worst case, it gives you the same performance as a binary search tree, but if the tree is big enough, what that is, it scatters the data across lots and lots of binary search trees. So you'll tend to get order 1 performance. Once they start filling up, it kind of degrades into log base 2 performance, which is still pretty good. Chaining is very easy to write and very easy to implement. It's a couple lines of code. We did that in 41. We did that in 41. These are the topics for this week. So I guess we'll just do linear probing. So okay, all right. So if so we can't just do this, right? We can't just insert in there. We have to see if the spot's available. Okay, so we go there. Okay, so step 1, see if the bucket is available. Step 2, go to the right, +1 buckets. All right, so this is linear probing. And we'll just do this in a loop. So for int I equals 0, I is less than hash table dot size, i.e. 10, I plus. Is going to yell at me? Maybe not. I don't know. It should be a size here. Doesn't matter. Okay, so we're going to try a maximum of 10 buckets, and if we don't get any of those, then sucks be us, right? Hash table's full. So I guess that's the first thing we can check for, right? So we can have a little size t count 0. How many buckets are full? Or how many things we've inserted, one or the other. Okay, so if we're going to go to insert, if count is greater than or equal to hash table dot size, then we will simply print out, sorry, hash table full. And continue or quit? Continue. Because theoretically they could erase something out of it. Okay. Right. And then down here, we'll need to decrement the count if we successfully delete something. Okay, so a little bit of sanity checking there, making sure it's not full. Okay, so we're going to go through, so if it's not full, then we should be fine. We're going to go through the whole hash table, starting at whatever bucket we are at. So current bucket equals this. And so if the hash table is available, so remember, if it's empty, we just have -1 for the social security number. So if that spot is currently available, then congratulations, we will insert into it hash table per equals C. And then we exit, break out of the loop. Otherwise, if the spot is taken, then we move on to the next bucket. So cur is equal to cur plus 1, and we wrap around if we hit the size of the hash table. And we need order of operations here, of course. Okay, so do you guys need to see this visually, or do you get what's going on here with the code? Does the code make sense to you, or do you want to see a little illustration of it? Want to find a visual? All right. Okay. See, these are our 10 buckets. Right. We got 10 buckets, which we can put stuff into. And so let's say that we're going to insert Crente. Crente is going to come in here, and his key is 45. Okay. So which bucket is it going to try to check first? And all of these are empty right now. They have error as the username, social security number, -1. What bucket is this going to search for first? Modding is based on the size of the hash table. That is correct. Yes, it is going to go to 5. So the bucket we search first. We don't search 0 because that would be your standard vector, right? You just start at the beginning, go to the end. That's order n, right? And so what we do is we say the bucket is equal to the key modulus the size. This is how we hash. Okay, so if Corente's social security number is 45, we check bucket 45, it's open. Okay, so we write in here Corrente 45, age of 20, whatever. Okay, now let's say that we're going to insert McCohen. Okay, so McCohen also has a social security that ends in 5. McCohen, his social security number is 125. And 120 with a 5 after it. And so we try inserting McCohen. We come in here, we see that this spot is not available. So this is where the 4 different algorithms vary. How do you handle this? If we're doing linear probing, we check the next bucket. Okay. If we're doing linear probing and that one's full, then we check the next bucket. Then we check the next bucket until we find one that's available, and we insert into there. With quadratic probing, we check 1 to the right, then we check 4 to the right, then we check 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Check 9 to the right, 16 to the right, so it jumps around more with quadratic probing. With double hashing, there is going to be some secondary function that'll take, the social security number and return like +7, and so it'll skip 7 to the right, 7 to the right, 7 to the right, 7 to the right. It's the amount moving to the right, depending on the methods. Yeah, for linear, quadratic, and double. It's just how many steps to the right we go. The rest of it's all the same. We just, with linear, it's always 1 to the right. With quadratic, it's 1 to the right, then 4 to the right, then 9 to the right, then 16 to the right. With double hashing, there's some secondary function, f of n, and that will tell you the step size you go to the right, like plus 13 or something. Well, it wouldn't be 13, it's 10, plus 3, or something like that. Okay. And so, and that changes based on your number. So Corrente might be +3 and McCohen might be +7. And so what that does, it scatters the data. So if you get a collision, it scatters the data. differently. With linear probing, you tend to get these plaque clusters of, like, everybody collides with each other and they go one to the right, one to the right, one to the right, one to the right, and it forms these like little islands of collisions. With quadratic and double hashing, it tends to scatter them across the array a little bit better, and when you benchmark them, which is what you're going to do, you are going to run a bunch of benchmarks and compare and contrast the running time of the different implementations on it. I'm confused on the performance of linear versus quadratic. You would think that the running time is going to be the same, right? Because it's just 1 to the right versus 4 to the right. You know, like, how is that going to result in a different running time? You know, as it turns out, you're probably not going to benchmark any difference between linear and quadratic, because quadratic does not work when the hash table is more than 50% full. And when the hash table is below 50% full, all of them are pretty fast anyway. So quadratic is sort of pointless, in my opinion. The Unix fast file system, I believe, uses quadratic hashing, and I'm not... Quadratic hashing, yeah. So, yeah, I'm not aware of anyone else that uses quadratic hashing. Let's Google it. Quadratic probing. Anyone have an example of it? Wikipedia. Dubious. Discuss. Linear probing has greater locality and thus better cache performance. Dubious. Discuss. It's not dubious. Linear probing does have better cache performance. Whatever. Limitations. No guarantee of finding an empty cell once it becomes more than half full. Yeah, that's what I just said. Yeah, I don't know. Frankly, I don't think I've ever used quadratic. Ever. Simply because it doesn't work when the hash table is more than half full. It's too big a downside to me. Double hashing is good though. Okay, so let's go back. Do you guys understand the graph? Like, if we're going to insert McCohen, then if we were doing linear, McCohen would go into here with a key of 1205. If we were to insert Mr. Bell, who also ended in a 5, then he would check 1 to the right and 1 to the right, and then Bell would go in here with his social security of 15, and Sarah Hang with her social security number of 16 would come in here, and that's full, and so Sarah would go into here, the SIN of 16, and so linear probing kind of builds up these big clusters of data. Do you guys kind of conceptually understand what's happening here? And then when you do a search, you come in here and you're like, oh, that's full, that's full, that's full, that's full. You're like, but wait a second, this is actually an order n algorithm. And so you would be right. You would be right. When a hash table gets full, it goes from order 1 time to order n time. Okay? When it's full. When it's empty. Okay? So, you have to just make sure the hash table never gets full. Comprendez-vous? So, it's a pretty ugly looking full there. Let's erase that. So when the hash table is full, it turns into an order n algorithm, right? Because imagine you got stuff in each one of these, and you're searching for, somebody go here, go here, go here, go here, go here, go here. You end up doing the whole thing anyway. So, how would you make sure the hash table never gets full? Same way that you make sure a vector never gets full. You reallocate. So when the hash tables hits some threshold, and this is actually a threshold you can set in the standard library implementation for an unordered map, you can set the threshold that it reallocates at. So when it hits 80% or 90% in the standard default, I think. Unordered map, max load. By default, it's 1. Okay, so when it gets completely full, it reallocates by default. So you can set the max load factor to be like 0.9 or 0.8 or something like that, so that when it's like 80% full, then double the size. And rehash. Yeah, when a hash table hits a certain size, you double it. And so a load factor of 1 is like, it's not good. Because if you look at the running time, this is load. I can't write. This is magic ink here. So if this is load, and load is the percentage full, right? This is the percent full that the hash table is. And if this is running time, what you see is that hash tables have really good performance. And then once they hit around 70, 80, 90%, they go like this. And so if this is like linear here, that's like order n. Hash tables start off negligible in performance, and then once they hit around 70 to 80, they start getting really bad, and then in the 90s they just explode down to order n. So I personally like using a lower max load factor, and you can also avoid that by simply pre-allocating. Do I have that window still open? I guess I closed it. CPP reference. Containers library. Unordered map. You can reserve in a hash table. You can sort of tell it in advance how much you're going to need, and so that's really useful if you have some notion of approximately how big your hash table is going to be, then it will pre-allocate it, and then you don't have to go through the reallocation process. So you don't have to allocate a new one, copy everything over, which is slow, So yeah, reserve is like a clue or a hint to the data structure saying, yeah, I'm going to need roughly 100,000, and then if you go over that, it'll rehash again. So you don't. It's not like you ever run out, but it's usually a good idea to do that to avoid needless things. So there is reserve, and that's actually really good. That's a really good performance optimization. So if you're in a code competition trying to get maximum speed, reserve a lot of RAM, and then your thing will go faster. Will the performance of reallocating a bunch of objects be horrendous? Yes, it's an order n, but you only have to do it once every n times, right? So like, let's say you have a hash table of size 10, right? To reallocate 10 people is order 10, right? It's an order n operation. But if you only reallocate when the thing gets full, then you only do it once every n times. So 1 times n is 1. So it's what's called amortized order 1. It's not exactly order 1. It means one out of every n times you do n work. So it averages out to constant running time, which is not exactly the same thing as constant running time, but for mathematical purposes it is. And so as long as you're doubling it every time, then the way the math checks out is that you can still call it an order 1 operation. Okay? So, can it be so full it just breaks the system? Yeah, like if you run out of RAM, that happens. It used to happen a lot more. The Apple II that I started coding on back in elementary school had 8K of RAM, something like that. And it's really easy to run through 8K of RAM. You know what I mean? Like your program is going to eat up a K or two. You know what I mean? Like Apple II RAM. No, not 16 gigs. Which RAM did it have? The equivalent of $5,500. Yeah, those things are not cheap. Memory, 4K, 8K, 12K. Okay, all right. So somewhere between 4 and 64K. Yeah. Cool. That's fancy pants RAM right there. Whole 64 kilobits of RAM. It's amazing. No one could ever use 64K. 640K of RAM should be enough for anyone, Bill Gates. So, yeah, nowadays when we've got, you know, my system here has 32 gigs of RAM. Like, for most non-supercomputing purposes, like, it's enough for this kind of stuff. You know what I mean? So, yeah, 32 is not even that much. It was like a little bit more than 16, so I bought it. DDR5 RAM's coming out, so whenever Alder Lake comes out, I might upgrade my system. It's gonna be a pain though. Tear everything apart, all that stuff. Get a new motherboard. I have to see if my cooler still works on it. So, but I might, because DDR5 RAM is pretty awesome, and it comes with PCI Express 5. It's pretty awesome also, so might do it over winter break or something like that, depending on availability of chips, right? Because that's a thing. Are you getting Windows 11 on release? So far, I'm utterly unimpressed by Windows 11. I haven't seen any reason to upgrade. At some point, they're probably going to do the thing where, like, they say the next Halo will only play on Windows 11, and that's how they've traditionally gotten me to upgrade my systems. They'll release a game that, for no other reason than they want you to, will only be compatible with the latest version of Windows. And I'm like, damn it, I want to play games. So Windows is just for gaming anyway. All my serious development work is on Linux. Okay, so does this make sense? Like, a hash table is just a big array, and you jump to the right spot. That's the key thing for hash tables, is that it's a big array, and you do a modulus with the key, and that takes you to the right bucket, hopefully. And if it's an empty hash table, it's boom, there it is. And so you can insert and search and delete and order one time. Now, when the thing starts filling up, is he a big gamer? Who's a big gamer? Your friend? Is he almost the exact same under the hood, just a new UE? Great. The UE is the worst part of Microsoft anyway. Oh, me? Yeah, am I a gamer? I haven't gamed since like last afternoon. I've been playing through the Quake re-release on Nightmare difficulty. It's been kind of fun. So you just jump to the right spot, and if you get a hit, boom, you're done. And then if there's a collision, which means that two different people have hashed to the same bucket, then you've got to resolve it. And linear and quadratic, I think, are pretty easy to understand. Double hashing, though, is going to require a little bit of explanation. So, so linear probing. If you try inserting McCohen into the database, and there's somebody there already with linear probing, you just go to the next one. You add one to it, and then you modulus, right? So you wrap around. That modulus, by the way, is not fast. A modulus operation is not a fast operation because it's a division, and division's the slowest operation by far. So there's some cool optimizations you can do. If you make sure that your hash table is always a power of 2, then you can use bit masking. You can use the bit operators. If you remember that from 41, you do a bitwise and. So what you do is you bitwise and it with the last. Like if your hash table is of size 16, you bitwise it with the last 4 bits, and that's the bucket. And that's one cycle instead of 80. So it's a lot of times you'll see people use power of 2 hash tables just because the modulus is usually the slowest part of it. It's actually not the hashing that's the issue, or it's not the collisions that is the issue so much as the fact the modulus is actually eating up most of the time. So power of 2 hash tables will resolve that. Quadratic probing, who cares? So double hashing, though, is kind of the main thing I wanted to talk about today, and we've got 20 minutes left to do it, which is fine. With double hashing, you have to make sure that your hash table is prime in size. So you can have a hash table of size 13, a hash table of size 17. If somebody requests a hash table of size 1000, which is obviously not prime, what you do is you use the algorithm you wrote for RSA to find the first prime number bigger than it. So, like I said, all of these things tie together, right? Like we've jumped back and forth in cryptography and cryptographic hashing, now real hashing, and the finding of prime numbers, which relates to RSA, and the whole reason why double hashing works, which I'll explain in a second, is because of the number theory stuff that we've done with prime numbers and how there's no cycle. If two numbers are relatively prime, Fermat's little theorem, it'll go through every possible number until it gets back to the original one again. So if you have a hash table of prime number size, then the way that this works is it'll end up checking every spot. Okay, so how does double hashing works? Well, the first part's the same. You just take the key, and if the key and the value are the same, then the value and the key are the same. So you take the key, modulus it by the size, you get a bucket 5. Oh, it's full. Okay, now what? All right. Well, rather than advancing one spot, like we do with linear probing, what we do is we do a secondary hash. And so what we do is we take the value, modulus it by r, and add 1 to it. And what is r? R is the prime number smaller than the size of the table. So if our table is size 13, then r is going to be 7, usually. It can actually be any prime number. It just has to be relatively prime. And so what we do is we modulus McCohen's social security number of 15 by 7. So like let's say, let's do a real life example of this. Double hashing. Okay, so let's say that the size of our table is 13, and then r is going to be the first prime number below 13, which is 7. It doesn't have to be, it could be any prime number smaller, but that's usually how we do it. So if we have this thing's sliding. Okay, so if we have a hash table of size 13, buckets, and just give me some numbers to insert. Okay, just type them out on chat, and I'll show you how it works. All right, so 5. Okay, so 5 modulus 13 is 5. Okay. 26 modulus 13 is 0. 26 goes into there. 923. You guys, all right. Either too easy or too hard, huh? 923 modulus 13 is 0. Okay, so we got our first collision. So we're trying to put 923 into here, and it collides. So rather than going one to the right, like with linear, what we do is we do a secondary hash. We have some function where we're going to pass in 923, and it's going to return 1 plus 923 modulus r. Okay, and is this covered up by the video? It is a little bit. Let's scroll that down. Okay, so there's a function, you pass in 923, the key, and the formula is 1 plus r, 1 plus the key modulus r. That's f of n. All right, that's our secondary hash. Okay, and that's going to give us the step size. So 923 modulus r is 7. 923 modulus 7 is 6. We add 1 to it. We add 1 because we might get 0, right? And the step size of 0 means you never leave the current bucket, which is bad. So we always add 1 to it. So, and that's also why r has to be smaller, because we're adding 1 to it, right? If you had a step size of 13, you'd also go nowhere. So 6 plus, okay, so 13. What? No, what? Okay, let's do that again. 923 modulus 7 is 6 plus 1 is 7. Good. So we're going to go 7 to the right. So we're going to insert 923. 1, 2, 3, 4, 5, 6, 7 to the right, and 923 is going to come into here. And the beauty of this is, let's say we insert the number 39. So 39 is also going to hash to here, right? 39 is also going to hash to this location here. But the secondary hash function is going to give a different step size. That's what makes it so beautiful. So the secondary hash for 39 is equal to 1 plus 39 modulus r. R is 7. So that's 5, right? So rather than going 9 to the right, this one is going to go 5 to the right. So 1, 2, 3, 4, 5. Oh, we hit 5. Go 5 more to the right. 1, 2, 3, 4, 5. And so 39 is going to come into here. So even if you have a bunch of things that all hash to the same location, because the secondary hash is a relatively prime number, you're going to get a wide distribution of like step sizes. And so they'll scatter over the array much, much nicer. Uh, 42, the result of that equation pushes value to another occupied spot. Doesn't run again yet. No, the secondary hash is always the same. It's 5. It's always going to be plus 5, plus 5, plus 5, plus 5. For 39. For 923, it's always going to be plus 7, plus 7, plus 7, plus 7, plus 7. Okay? So the step size is always the same. You can pre-compute it if you want. So if we're going to insert 42, let's see. It's going to be 3, right? Okay, so 42 is going to come into here. It's 39. 42 minus 39 is 3. 24, okay. So 24 is 9. It's going to come in here. No, 11. 24 minus 13 is 11. No. It just plus 5s until it finds another open spot. Yes. And because our hash table is size 13, and anytime you advance plus 6, plus 6, plus 6, plus 6, plus 6, because it's relatively prime to the size of the hash table, which it has to be because 13 is a prime number, it will eventually cycle through the entire thing and find an open spot. So it's guaranteed to find an open spot. Okay. Doesn't matter what the step size is, as long as it's between 1 and 12, which it will be, then it will eventually cycle and find an open spot. Because the downside is your hash tables have to be prime size. So you can't get exactly the size hash table you want sometimes. Sometimes you want to have a hash table of size 1,000, and it's like you're going to get a little bit more. But the big downside is if you have a prime hash table size, it's not going to be a power of 2. And power of 2 hash tables are much, much faster because you can use bit masking to just bit mask off whatever power of 2 the size of your table is to do the modulus. Do you guys see that? Like rather than doing a modulus by 2, modulus by 2 is the same thing as saying ampersand with 1. So if you have x modulus 2, that is exactly the same thing as saying x ANDed with 1. Right? If x is 7, 7 modulus 2 is 1. 7 is the same thing as 4 plus 2 plus 1 in binary. Bitwise ANDed with 1 is 1. A bit mask, this is something like 70 times faster, depending on the architecture. It'll kind of give you an order of magnitude. Could be 10, could be 100. It's kind of a ballpark figure. Okay. You guys see that? So it's actually really nice to be able to have a power of 2 hash table size, and you lose that when you do double hashing. And so that's what makes this benchmarking assignment that you guys are going to have interesting, because you're gonna benchmark. Did you guys do the hash table benchmarking in 41? Did I do that with you guys? I did. Damn. Oh well. Sorry, I'm not going to do it again then. Be too easy for y'all. I guess we could. Copy paste. Maybe we could compare three things. We could compare linear probing with power of 2 size. You know what I mean? Like make sure that your array is a power of 2, because then you can do it with bit masking. Double, I'm pretty sure we didn't do double hashing, right? Did we do double hashing? I don't think we did. And then we can do chaining. Okay. And so chaining is the world's easiest to write hash table implementation. You did linear and chaining, right? Yeah. So we're gonna kick it up a notch, and we're gonna do linear probing with a power of 2 size array. Do double hashing. We're gonna do chaining. Okay. So we'll have to pick sizes that are powers of 2, I guess. And then for double hashing, I guess they'll get a small advantage of using a little bit more RAM, right? So rather than 1024, you'd be 1025 or 1027, you know, whatever the nearest prime number is, right? So double hashing would get maybe a small advantage in that regard because it can't have a power of 2 size. But time to relearn shell scripting. Yeah. Okay, but this is what computer science really is all about, right? You need to know theory and you need to know big O, because if you get your big O wrong, your code's gonna just suck. It's just gonna be bad. It's gonna be DMV level performance. You know what I mean? Like you need to get like your big O in place. But then once your big O's in place, like we were talking about earlier, what's faster? Quick sort, merge sort, heap sort? There's actually going to be real performance differences once you're all in the same big O ballpark, right? And for this one, they're all the same big O. Chaining, maybe not. Chaining degrades, the performance of chaining degrades from order 1 to order log base, wow, what is that? Order log base 2 of n, like that. If you use BSTs, which you should. For some reason, a lot of textbooks do it with linked lists, and then it goes from order 1 to order n. I don't know why you do that. I honestly, I don't get it. Make a BST at each spot. Okay. So, 10 minutes left. Yeah. So chaining has a better big O performance, worst case time. So be it. So be it. All right. So what I'm going to like to see from you is a table. The end product of your code is going to be something like this. It's going to be size, maybe sizes up here. Size up here. Size 1024. Size 2048. Size 4096. Okay, and you're going to have linear with bit masking. Do you guys understand what I mean by bit masking? Like, you all know the bitwise and, right? So rather than modulusing by 4, you do x ANDed with 1, 1. Right? So this, or 3, same thing. Instead of modulusing by 8, that's the same thing as x bitwise ANDed with 1, 1, 1. Okay. So, yeah. So modulus by 8 is the same thing as bitwise ANDing with 1, 1, 1. So you'll need to do your linear probing using that, because we want linear probing to have a fighting chance of winning, right? And the fastest hash tables I've seen actually use this approach rather than double hashing, which in theory is better. So you're gonna have a series. This is basically what you're going to turn in. You're going to turn in 1024, 2048, 4096, 8192, 16K and change, 32K and change, 64K, 128K, 256K, 512, and a million. Okay. And you're going to put in the running time, like 0.1 seconds, and this one's 0.1 seconds, and this one's 0.2 seconds, or whatever. So you're going to just fill it in, linear, double, and chaining. Chaining. Okay. You're just going to fill it all in. 2, 1, 0.3. Yeah, something like that. Okay. So that's your task. You're going to have a week to do it. There's a couple different moving parts here that you should figure out, like how do I generate the input files, right? How do you graph it? Because I want to see a graph too. I want to see you plotting it. Okay. So I might even give you. I'll give you a week and a half on this because we're kind of out of time today. So don't stress out too much about it. It'll be due two Tuesdays from now. Your competency exam is up, and so make sure you don't miss out on that. It is on modulus, but not on hash tables because we hadn't talked about hash tables yet. The next competency exam on modulus, I guess, will include hash table modulus as well. So yeah, you'll have a week and a half to do this, and it's really the kind of assignment that will prepare you for grad school. A lot of grad school is this kind of stuff. Like you implement an algorithm 3 different ways, you do your best to optimize it, and then you hammer the hell out of it. You run it over and over again. You write a script to run it over and over again, collecting the data, putting it into Excel or some other program to graph it, and presenting. Like, I don't know how many times I would stand up in front of a room of students. It's grad school, so it's like 10 students. It's not a lot. Like typically our grad school classrooms were in conference rooms. Like they're not in classes. Like they're just in a room about this big. People are sitting around a table and you take turns. Okay, Kearney, you're week 5. All right, cool. And so I would work my butt off and implement an algorithm 3 different ways. Hammer it. Just like really go at it. Running things, collecting data. Then I'd put it into a PowerPoint presentation and throw it up on the screen and walk people through it, and they'd ask me questions like, all right, why are you using bit masking instead of modulus? I'm like, it's a lot faster, Well, doesn't the optimizer do it for you? I'm like, maybe. Maybe you did. I didn't check that. I didn't want to risk the fact the optimizer wouldn't, turn a modulus into a bit mask, you know what I'm saying? So, how many tries do you get again? On what? How many tries do you get? Oh, on the competency exams? 4. Yeah, you can take it twice, and then if you fail it twice, then you have to go into the tutorial center and ask for Corrente or Mincarelli for help. Yeah, or sorry, Valenzuela for help, and he'll walk you through the topics on it. So it's you don't take it thinking that you can immediately retake it. It's going to be a different test every time. You should do benchmarking absolutely with the optimizer on. The running times are almost pointless if you have the optimizer off, simply because a lot of the standard library stuff is so poorly written out of the box. Like if you just use like a linked list class or whatever, like it generates super bad inefficient code. You really have to have at least O1 turned on in order to have any reasonable numbers out of it. Like if you have the optimizer off, that's saying I don't care about running time. That's what O0 means. I literally don't care about running time. I'm just trying to get my code working. O1 means, hey, clean it up a little bit for me, eliminate obvious redundancies. And that's actually usually good enough to get going, but I would only do these things with -O3 on. O3 is your friend. Always have that turned on when you're benchmarking. G++ main.cc-O3, yeah. Mm-hmm. The competency exam is just modulus problems, that is correct. In different ways, in different formats. RSA, for example, is a modulus problem. So make sure you understand the RSA algorithm. First, you don't succeed, try compiling with O3. If your code's not correct, O3 is not going to help. But anytime you're doing anything with optimization, like if you ever look at the assembly that a compiler makes with the optimizer off, it's really, 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 really bad. It's horrendously bad assembly. Like, as somebody who writes assembly professionally, because I'm a professor, so it's professionally, I'm professionally offended by how bad the assembly is coming out of the compiler. And the reason for that is because it just relies upon the optimizer to get rid of obvious inefficiencies. Like, it'll do horrendously inefficient stuff because it knows that the optimizer will come in and be like, yeah, let's just get rid of all that. So, yeah. Yeah, let's see here. Yeah, the current code that I just wrote there, -s, word count, main.s. It just generated 2,221 lines of assembly. With the optimizer on, it generated, well, 1987. But that's not really the whole story. If you come in there and look at it, there's a huge amount of wasteful operations that just get eliminated, and you'll see, like we saw what, a 400 times speed difference or something. Like, it can be really impactful. Usually the optimizer is going to give you about an order of magnitude thereabouts. That's kind of the ballpark. It'll give you an order of magnitude speed difference. But like we saw with the Josephus problem, like, it can make a really, really big difference. Okay, you want to copy it? Yeah, okay, so copy main.cc into public. And so if you want to make a copy of the file from today, copy /public/main.cc to your current directory. That will overwrite whatever main.cc you have there. So if you want to give it a name, you can call it hash table notes.cc or something like that. Okay, and if you want to delete it, do that. If you don't want to delete it, don't do that. So in public main.cc is the notes from today. Okay, and I always put my code up on the server for you guys to copy. So all that is, though, is the first half of hash tables, right? It's not the second half. It's not the meat. It's not the hard part. The hard part is, doing the double hashing. It's not even that hard, really, or the chaining or whatever. Like, when there's a collision, that's where the interesting stuff comes in with hash tables. Hash tables are quite boring if there's no collision. It's very easy to write. Okay, so yep, you'll have, what is it? 7, 8, 9, 10, 11, 12 days to do this assignment. Don't wait to the last minute. It is a fair bit of coding, but it's a lot of benchmarking. You're gonna run your program over and over again, generate a bunch of data, and we'll talk more about it on Tuesday. But if you wanna go ahead and start implementing linear probing with power of 2, double hashing with a prime size, and chaining, do it, and that'll prep you for Tuesday. Okay. Copies tilde public. No, tilde is your home directory. So if the front slash here means root directory, so public is in the root directory. If it was here, then that would mean in your home directory, the public directory in your home directory. Do it earlier, you might lose speed intervals. Does it the same the night before? Yeah. When everybody's hammering the server cries. So 2 Mondays from now is not going to be a good time to be trying to do stuff on the server. Will we get a refresher on shell scripting? Yeah, we'll talk about all that on Tuesday. Okay. So for now, just go ahead and write your own algorithm for insert, search, and delete for linear, double, and chaining. And have that done by Tuesday, and then you'll be in a good place. Okay. You're going to have to do it at some point. Might as well do it now. You got a weekend to do it. Next weekend probably is a good time to be doing the benchmarking. This weekend, hash it out. It's not, like, you can see that the amount of code is not, it's not really that bad code-wise. Well, we didn't get to the bad part. It's not really that bad. Okay. All right. That's it for today, guys. Have a good weekend. Hash it out.